There's a practice problem on the slide. You can think about that. Try to solve it. Try to prove it. Yeah.
The question 4 on the assignment, I'm not really sure how to analyze like the exponent.
The exponent?
Like, the exponent of the exponent. I was in the math help call this morning and the guy didn't know how to do it either.
In what this morning?
I was in a math help call like in the tutoring center. And
Oh, the online tutoring center?
Didn't know how to do it either.
Oh, the TAs didn't know how to do it?
No.
Okay. Yeah, we can talk about that. Yeah.
Okay.
And there's people from the last class that asked me about question 4 as well. So I told them during my office hour 5 to 6,
Yeah.
I'm going to be helping them with that.
Yeah, I'm very stuck on that one.
Okay. All right. So questions 4 and 5 were tough? Okay, on the slide I have a Math 135 question. So have you guys had a chance to think about it? Anyone thinks they have the formula? Yes, Paige?
Okay, I didn't just like summation notation.
Okay, but summation notation isn't enough. If you just write that as the sum of k times k factorial from k equals 1 to n, I think that's not enough because all you've done is converted it to, I mean, when it says prove that that's correct, how are you going to prove? All you're doing is changing the notation. You haven't found a closed form expression for this, for what you have here.
I mean,
Arnav?
like just carrying forward that idea, you might as well prove that by induction and show that it's true for n plus 1. You assume it's true for n, and then you prove that it's true for n plus 1.
I think you need to do a bit more. Now, yeah, I apologize. I know the question. I think the question, this is a question from a previous version of Math 135. I would have adjusted this question to say find a closed form expression for this. Because if you have a summation from k equals 1 to n, that's not a closed form expression. But this is the way the question was asked, and the answer was not in summation notation. So it's not enough to just prove this by induction. Grayson?
I think I found the expression is n plus 1 factorial minus 1.
Okay, good, good.
And yeah, I don't have an induction proof for it. I've got a proof that relies on keeping the indefinite sum, so I don't know what that's.
Oh, okay, okay, but you converted that indefinite sum into, okay, that's also what Arthur did in last class. So we did have someone in last class figure that one out too. Okay, let's get to the point here. So I did some rummaging through an old computer of mine, and I found my files from way back when I took Math 135 here at U Waterloo. And for assignment 1, this was due on Wednesday, 19th of September. We had a 1-week orientation week, so we started in week 2 after Labor Day. So this was week 1 assignment, due at 8:20 a.m. I removed the year here. But this was assignment 1. Okay, prove this by induction, prove this by induction, prove this by induction, multi-paragraph game theory question. Using the fact that d by dx of x equals 1 and the product rule, prove by induction that d by dx of x to the n equals n times x to the n minus 1. What is that, the power rule or something? Yes. They ask you to prove the power rule by induction. Okay, and then we go through the solution. Oh, and then there were 7 questions on this assignment. And then there was a bunch of other recommended problems. One of them was this. Find an expression for 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial, blah, 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 and prove that it's correct. So this was week 1 of the course. And you can see in the solutions, it's induction, 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 game theory, but proven using induction. Recommended problems, proven using induction, induction. This product notation, you're doing that in this week 7 assignment, right? Assignment number 6. So that product notation, we had to do that in our week 1 assignment. And then induction, and that's it. So it was just a bunch of induction problems for week 1. Lots and lots and lots of them. So let's get back to here. We have this expression here, and we don't know what the closed form expression is yet. Converting it to summation notation, I think it's not enough. You're just changing the notation. You haven't really done anything there. So here's the proof strategy if this were to come up on an exam. Okay, you want to find an expression for it. How are you going to find an expression for it? One of the ways to do that is to just see what that expression looks like for n equals 1, 2, 3, 4, right? Now, forget about what Grayson said for a second. I just want you to look at these numbers. When n equals 1, n equals 2, n equals 3, n equals 4. What do you recognize about these numbers? 1, 5, 23, 119. What do you recognize about those? Arnav?
Yeah. They look like they're 1 less than the factorials. Like
Yeah. Okay.
6 minus 1, 24
Yeah.
minus 1, 120 minus 1.
What's 5 factorial? Yell it out.
120.
120. Okay, that was what Marissa. Okay. 4 factorial?
24.
3 factorial? Okay, so there's more and more voices coming as I do smaller and smaller numbers. 2 factorial? Okay. 10 factorial? Oops, I don't have enough space here. Oh, that was...
Where's the eraser? All the way over here.
Okay, so if you know your factorials, I mean, if you're a student that just loves math, like I did as a kid, I used to just play with my calculator, press a bunch of buttons and see what happens. And then I would just remember what happened. And so the factorials, 6 factorial, anyone know? 720, yeah, okay, good. So here you have 5 factorial minus 1, 4 factorial minus 1, 3 factorial minus 1, 2 factorial minus 1. So you have the factorials minus 1. So that's a conjecture, right? We think that, at least for small values of n, we're finding that n factorial minus 1, or n plus 1 factorial minus 1 seems to be the formula. So let's do this by induction. We assume that this sum over here on the left equals k plus 1 factorial minus 1. Okay? In the previous slide we had 120 minus 1, 24 minus 1, 6 minus 1. We had all the factorials minus 1. So let's assume that that's true, and then consider n equals k plus 1 and see if this induction hypothesis gives us what we wanted. So here we have exactly what we started with. This is 1 factorial plus 2 times 2 factorial, blah, 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 all the way up to k plus 1 times k plus 1 factorial, and then this whole thing on the left, we just assumed that that equals k plus 1 factorial minus 1. So here we plug that in. We have k plus 1 factorial minus 1 plus k plus 1 times k plus 1 factorial. That part, so this part is just from here, and this part is just from here. So now we just rearrange it a little bit, and we end up with, we have n equals k plus 1. So we have n plus 1 factorial minus 1. The induction is pretty easy once you figure out what it is that you want to prove. You got it? Okay, so you're comfortable. In the exam, if they say find an expression for something and then prove that it's correct, one strategy you should not be afraid to do is to just plug in some small numbers and see what the expression might be. Okay, Grayson, the way you did it was you started with that summation notation and then you played around with the summation notation until you got that.
Yeah, so basically, it's 1 times 1 factorial, 2 is 2 factorial, so you replace the 1 with 2 minus 1, 2 with 3 minus 2,
So you started with the sum of k times k factorial from k equals 1 to n. And then what did you do?
So we'd have 2 minus 1 times 1 factorial.
2 minus 1 times 1 factorial? What?
Yeah. Plus
Where does that come from?
I'm just starting with the indefinite sum we're given.
Okay, we have that. But where's the 2 minus 1 coming from?
Oh, if you want to do it that form, replace the k with k plus 1 minus 1.
Okay, so k equals 1. This is now going to be k plus 1 minus 1.
Yes?
And then another one for k factorial.
No, leave the k factorial.
Leave that, yeah. But how did you know to do k as k plus 1 minus 1?
Because I was looking one step ahead, and you can rewrite this as k plus 1 factorial minus k factorial.
Okay, so you also did what was suggested in the solutions, which is to figure out what the formula is and then try to prove it. How did you know what one step ahead was? How did you know the next step?
I was just looking at the 2 times 2 factorial that's really close to being just 3 times 2 factorial, which is something I can work with. So how do I convert one to the other?
The 2 times 2 factorial, so this part.
Yeah, if it was 3 times 2 factorial, it would be easy. So how do I convert that?
So why would it be easy if this was 3 times 2 factorial?
Because that's just 3 factorial.
Oh yeah, okay, yeah. So 2 factorial is almost, 2 factorial times 2 is almost 3 factorial, except we have a 2 instead of a 3. And 3 times 3 factorial is almost 4 factorial, except we have a 3 instead of a 4. That's what you're saying?
Yes.
Okay, so then you wanted to convert this into that form. So instead of k factorial times k, you wanted k plus 1. And then you did the how many people would have done that on an exam? Okay, so that's why I'm giving you this alternative proof. Instead, just plug in some numbers. If you recognize, this is the solution that they gave us when I took this course, and they're just hoping that you would have played around with numbers enough in your life that you know that 5 factorial is 120 and 4 factorial is 24. Okay? So we can finish this proof though. So I don't know if I would have thought of that. Like, just because this is close to 3 factorial and that's close to 4 factorial, the thing is that it's not. So I would have probably tried to play with this directly. And Arthur in my last class also wrote it as a summation notation, then played around with it and ended up getting the right answer, just like you did. But I don't know if he used this trick. So there's multiple different ways you can prove this. And if you can see the tricks, then good for you. But I asked who's going to be able to figure that out on the exam. No one said yes. So this is just a suggestion for you. But let's just finish this off, just so that. So you have k plus 1 minus 1. Then what do you do?
Then you multiply it out, so you end up with k plus 1 factorial minus k factorial. And you can split the sum if you want.
So you have k, say that again?
You have the sum for k plus 1 factorial.
Yeah, k plus 1 factorial. Yeah, because you have k plus 1 times k factorial. Yeah, that's k plus 1 factorial. Minus
the sum for k factorial.
The sum from k equals 1 to n of k factorial. Yeah.
And now, re-indexing, you can turn that left-hand sum into a similar sum as the right-hand side.
Okay.
Yeah. So this is why I said it still depends on the indefinite sum.
Oh, so you still have a sum at the end?
No.
Okay.
I never turned it into summation notation.
Okay.
Which is why I don't like the way I was trying to prove it.
Oh, I see.
This is just how I have a statement.
Okay, so this is the way you were thinking about it.
But I definitely would prove it with induction.
Okay, yeah, okay, good. Good, okay, so we'll all prove it using induction when it comes on the exam. Okay, good. Okay, so Arthur and Brian in my last class started it like this. They didn't do plus 1 minus 1, instead they did like plus k factorial minus k factorial.
Yeah.
And that ended up being the same. That's exactly what you did. You did plus k factorial minus, but they didn't do it here. They just did this plus k factorial minus k factorial. And that's because they looked at this pattern, they saw what the pattern was, and then they decided they wanted to prove they wanted to prove this. And in order to prove that, they thought that it would be smart to do plus k factorial minus k factorial. And then they got to this stage, and then they actually turned this into this, using some manipulation of the sums.
Yeah, you changed the balance a little bit.
Yeah, and it's not obvious. I don't know if I would recommend doing it that way. This induction proof, that's how many people would feel comfortable with this induction proof on the exam? Okay, so more than this proof at least. That's the one I would recommend. All right, so let's get on. We have, does anyone still have to submit their regrade requests for the midterm? Okay, how many people already submitted it? Good, okay, good. Because I think a lot of people are getting marks awarded back for questions 10 and questions 4. So at least for those ones, it might be not a bad idea to submit a regrade request. Try to do it as soon as possible because, well, it's due on Wednesday now, but you want to do it as soon as possible while the midterm is still fresh in your head. Okay, how many people are done the assignment? Okay, good. I was originally going to assign these readings, but I saw in the last class that a lot of people weren't yet done the assignment, so you probably want to finish your assignment first and then do the readings. But there's a reason why I'm talking about the next chapter's readings right now. This is pages 110 to 121. It's 11 pages. It's 11 pages, so it sounds like a lot, but it's actually not too much because the first section, 6.7, I think that's just the prime number stuff. So when I proved that a cubed divides b cubed implies that a divides b, how did I prove that? I prime factorized a and b, and then I said that the prime factorization of a cubed has to divide the prime factorization of b cubed, and therefore a must divide b. So you already know the prime factorization, which is chapter 6.7, 6.8. Proof that there's an infinite number of primes, you've already proven that, right? You've already seen that proof in the course. And then there's Euclid's lemma, or Euclid's lemma. The one where I showed you that proof where if m divides e times n to the 4, and m doesn't divide n to the 4, then it must divide e. So you remember that proof as well. So a lot of 6.7, the remainder of chapter 6, I think is just prime factorization stuff, which a lot of you are already familiar with. And then there's chapter 7. The whole of chapter 7 is just like 2 or 3 pages long, right? It's just linear Diophantine equations. It's like 2 or 3 pages long for the whole of chapter 7. So although it's 11 pages, I think it's not too much in terms of the content. And I think it would be a good idea to get that stuff done as soon as possible because, in my opinion, chapter 8 is the hardest chapter of Math 135. Okay? And chapter 8 relies on pages 110 to 121. So if you want to get ahead with 110 to 121, it will set you up well for chapter 8. Because I'm warning you, chapter 8, it's just the hardest chapter of 135. After that, then things I think will get easier. Chapter 9 is just RSA cryptography. That's just an application of everything we already learned. So if you understand divisibility, you understand chapter 8, like Fermat's Little theorem, and GCDs and stuff like that, then chapter 9 is going to be very mechanical. Every exam so far, if you look at all the previous exams on MathTalk Exam Bank, they all have one RSA question, and you can see it's always the same kind of thing. It's just plug in numbers, right? It's like, do RSA for P equals this, or P equals that, and you just have to do the RSA. So it's just an algorithm. You memorize that algorithm, you just do it. Okay, or you just describe the RSA protocol for a given number. So that, chapter 9 should not be hard once you have all the foundations. Chapter 10 is just complex numbers. So how to add complex numbers, how to subtract complex numbers, how to multiply them, how to divide them. There will be some difficult proofs. There might be some induction proofs and stuff like that. But in the end, it's just arithmetic using complex numbers. Typically in Math 135, the students find that one quite easy, that chapter. And then after chapter 10 is just polynomials. So chapter 8 is really the last chapter where it's really tough. And it's tough because you have to know every possible theorem. There are going to be proofs where they ask you to prove this or prove that. You have to know everything about GCDs, co-primeness, prime factorization, divisibility. You have to put it all together. So that's why I'm recommending to try to read ahead for pages 110 to 121. Try to do that as soon as you can. So Wednesday, you've got to submit assignment 6. And then I would suggest Thursday as soon as you can. Assignment 7, take a look. Start it as soon as you can. And that's going to be covering pages 110 to 121, which I'm recommending to try to read as soon as you can. All right? Now, I know it's tough, okay? I understand that life is busy now. I was here just like you as a Math135 student. I understand that there's no free time. I understand you finish the Math135 assignment and then you have the 137 assignment. Then you have the Mobius quiz. Then you have the 137 Mobius quiz. Then you have the CS midterm. Then you have the speech communication speech. Then you have another Math135 assignment. And it never stops, right? It just never stops. And I know, because I've been there. That's why I know what you're going through. Okay? And it's the same for me. I'm also working around the clock. Okay? I'm here from morning until office hours 5 to 6. Sometimes they end at 7:30. Then I'm doing piazza until like 2 o'clock in the morning sometimes. And then, you know, marking the midterms. I was up until 8 a.m. marking those midterms. I'm also working around the clock. I'm working on weekends. I'm working left, right, and center. So I know we're all doing this together. Okay? We're all in this together. Okay? So here's a fun time for us. Okay? Here's guess my salary. Okay? I'm just curious. And if you already know, because I accidentally told you in the office hours, then don't say anything. I'm just curious. Just guess my salary. In the other class, there's tons of people just yelling out numbers. Pardon me?
140,000.
140,000? Okay. Anyone else?
160.
160? Oh. Okay. How many people think it's in that ballpark? Per year?
Okay.
Yeah. 140, 160. Anyone else?
Minimum wage.
Minimum wage?
Yeah.
I think I might be happy if it was minimum wage.
Okay.
It's less than minimum wage. Okay. So here's my contract. Is this number visible? Not really? Okay, I blew it up. So for teaching 2 courses, $17,644. Oh, sorry, $17,644. And so this is actually because I'm teaching 2 sections. So for 1 section, you'd get $8,822 per section. And because I'm teaching 2 sections, I have this times 2, which is $17,644. So if I were to teach 2 classes per term for 3 terms, then in the whole year, I would be getting triple this, which would be less than $60,000. So much less than the 140 you're guessing and the 160 you're guessing. And if you do add up all the number of hours, it probably is less than minimum wage, because I'm working like, from when I wake up until when I sleep, I'm working, right? So the number of hours divided by, the amount of money divided by the number of hours, it probably is less than minimum wage. And you can also see here the date of this contract, 20th of August 2021. It's like 10 days before September. They suddenly asked me, hey, we want you to teach Math135. We know you haven't taught at UW since 2008. We know you've never taught 135 before, but we gotta get more instructors, okay? These classes used to be double the size. You notice there's gaps in the seats, right? With COVID, they wanted 1 spot between every 2 people, at least. So they ended up making the class sizes half the number of people per class. That means you have twice as many classes, which means you need twice as many instructors. So at the last minute, they're like, oh, we want to teach this in person 10 days from now, can you start teaching 135? Okay, so it's not a lot of time to prepare, and it is my first time teaching Math 135, and I haven't taught at UW since 2008, so it's been a long time. I just wanted to, I don't want people that have, how many people want a career in academia? Well, no one puts up their hand after I told you the salary, right? Okay, well, if you are interested in academia, it's not that bad, okay? Salary disclosure 2020, if you go to University of Waterloo website, you can see that there's some professors earning $336,000 a year. Okay, some of them earning 232, some of them earning 199. Oh, I feel bad for that person. It's always, the person that's in third place is usually happier than the person in second place, because the third place person's happy that they didn't come in fourth, but the second place person is upset that they didn't come in first. So, yeah. Couldn't they have just given an extra $700 a month just so that they could get 200? So yeah, Ray LaFlamme, that was my undergraduate thesis. When I did my undergraduate thesis in my fourth year, he was my supervisor for my fourth year thesis. And his PhD supervisor was Stephen Hawking. So has anyone ever read Brief History of Time? Who's heard of A Brief History of Time? Stephen Hawking's Brief History of Time. So in that book, there's a whole chapter called The Arrow of Time, which is about Ray LaFlamme. Okay, so, and he's not even the highest earning professor at University of Waterloo. So it is possible to get a high salary here at UWaterloo. Salaries can be high. I just happen to be at the bottom of the ladder, right? Because I'm just new here. I just came back after more than a decade away. And so this is my first time teaching at UW since 2008. So I've started at the bottom. And you know, from the first day of the lectures, I told you I had this history as a researcher all around the world. Okay, you see some prestigious places here. You see Oxford, you see Harvard. There's a lot of prestigious places where I've worked. And so you might wonder, why would I give up everything only to start back at the bottom here? So who thinks they know why? Yeah?
Does it mean you did pretty much everything you...
Oh, I did everything else, so I'm done all that. Now I have to try something new. Yeah. The truth is that it's because I love teaching, and I love to help people. I've been where you are. I struggled. I was up until 4 o'clock in the morning throughout my entire undergrad. I had headaches. I had, I had anxiety. I had all of the things you're going through. And I was able to get through it, and I figured out how to get through it. And all those skills that I learned over all that time, I think it would be cool if I could pass that on to other people so that they can have the same success that I had. So I don't care about the salary. Whether it's 17,000 or 20,000 or even nothing, it doesn't matter, right? I've already had my fun. I've already had this fun, and now I'm going to have even more fun by teaching. So I really care about teaching. I'm only doing this because I really love it, okay? I'm not doing this because if I don't do it, I'm not going to get my next research grant and the university won't fund my next experiment or something like that. It's literally because I just love teaching. So because of that, I'm going to ask for feedback on what I can improve, because if I've given up that whole life to do teaching and then I'm not doing a good job of it, then that would be quite a waste. So if you have your phones or laptops or whatever, you can go to Learn, and then to Submit, and then to Surveys, and then to Nikkei's survey. It's 4 clicks, and you get to a survey. The last class, they finished it in about 5 minutes. We're all friends now, okay? I'm not just your instructor. We're all friends, so don't be afraid to tell me a little bit about yourselves, about your hobbies, interests. Just let me get to know you a little bit. When I get to know my students, then it's much easier to teach them. So just try this out for 3 or 4 minutes, anyone that's able to. If you're not able to, then maybe you can think about what you want to say and do it later if you want. But in the last class, this turned out to be a fairly useful exercise.
I already finished it.
Oh, you did it?
Sent me a message on Teams.
Okay, you were online. If you were online, then I might have sent it.
I did it within like 5 minutes.
Some people saw it on Learn. Okay. If you saw this on Learn, because you were looking at Learn and trying to see what else updates there were, then you might have already done this. But for everyone else, yeah?
For like the past 2 weeks, my GitHub hasn't been updating. Have you been posting to the GitHub?
No, I haven't.
Oh,
not lately. I'll catch up on that. I fell behind during the midterm season.
Because like...
I know. Yeah, I haven't posted there since like lecture 15. I know.
No, a little bit ago, my main computer wouldn't update, and my laptop would, so I didn't know if both of my computers were glitching out.
Yeah, but this is not computer dependent. This is it's just about GitHub not being up to date. So that makes sense.
Yeah, no, like a week ago, my laptop had more slides than my computer. So like my computer wasn't updating, but my laptop was, so that's what it was just maybe like
If you want these all the time,
You were able to get online, Justin, on the phone?
I'm trying.
Yeah. Vihang? Is it working? Okay. During this time, during this time, I'm going to think a bit about what to say about question 4. So question 4, what part was that? Part A of question 4 is the hard one?
Yeah, question 4 is hard.
For question 4, which part was it?
I was just trying to do the inductive stuff, and I just like
So that's
put
part
in.
A?
Yeah, part A.
Okay. Yeah, well, it seems a lot of people had trouble with 4A, so I'm going to review.
so like it's white line and we got it, you should get it.
You found the SAT, but like certificate of correctness for it. You go like for whatever that theorem is called, like is it invasive? I want to say. Yeah. Like I said, like it's, you know, it's you got the difference of the A and B.
No. Do you get what I'm trying to go? Yeah. So I was putting in 3, 4, 5 or stuff.
Okay, how many people are done? Okay, how many people still working on it? Okay, how much more time do you need? Okay, how many people are still working on the survey?
Like 2 minutes.
2 more minutes? Okay. Okay, I'll time 2 more minutes. If 2 minutes isn't enough, it's okay if you need more time, but I'll just go on with the lesson after 2 minutes. Because I have to balance between the people that are done and the people that are not done. You got it working? Did it work?
Yeah, I can't even log in. So.
It's weird. Vihang's doing it.
Yeah, now I can't even like.
Is it an old phone?
No, not really. I mean,
Pretty good. Yeah.
like.
Don't worry, like I would have the reviews and then I literally went for it.
I think the question that you started, so you might want to do that, or just yeah. Yeah. So the GCE is 51 51 is the last yeah, based on, I think they do yeah, yeah. Yeah, 10 days. I think that's probably enough.
10 seconds. Okay, so that's 2 minutes since the time I asked. Are you still working on it, Mia? Still need a bit more time? If you need a bit more time, that's okay, but since a lot of people are done the survey now, then let's just move on to the results. And, you know, I'm going to show you the results in real time. I think, hey, you guys don't need to talk anymore, right? So, survey results. If I looked at this at home and then filtered out all the bad reviews and then only showed you the good ones tomorrow, that wouldn't be fair. So I'm just going to look at them right now. Whatever you wrote just now, that's what's going to come up here. This is dangerous. What if there's some scathing reviews here? It's going to go on the camera and everything. But anyway, so we go to learn. So ideally, I would just be able to click this, but for some reason.
It blew up last time. Who knows if they'll do it again?
Okay, so learn.uwaterloo.ca may be harmful to your computer and data. Yes, okay. Oh, two-factor authentication.
I don't know why it does that.
I got this to work in the other class, actually. So
F11 is what you want to hit.
F11, all right. Okay, here, so, okay. All right, 18 people in actuarial science. Good. Many of you are going to be earning more money than me. Actuarial science, very good. So you like statistics? Okay, there's some people doing data science, combinatorics. Good. I like combinatorics. Statistics, very good. CS, 14 people. Okay, good. All right, let's see. We have a very diverse group of students here. We have dancers, drawers, gamers, tennis players, runners, going out with frienders, basketball players. Very cool. It's very cool to have such a diverse group of people here at Waterloo. Crypto, coding, competitive math, programming CS projects, scuba diving, cool. Chess, basketball, dance, gym, baking. We have a little bit of everyone here. That's great. Okay, I was really worried about this one, about the music, because I think I've come from a different place. I come back to Waterloo and I thought that the music is something very unconventional, which the other teachers aren't doing. And I was worried that some people might be like, oh, this is too loud, this is, I don't like this, this is, no, I'm trying to do that to pump everyone up so that after a whole day of boring classes, everyone's pumped up. And it seems like no one actually said that they want me to stop playing music. So that's a surprise, and that means that what I've been doing all along. I was really worried that people might not like the music. So I'm happy that I can continue to do that. There's no one that said that they want me to stop. Okay, now these responses is quite big, so how do I fit that all into one screen? Can you still see that?
No. See, yes, read. Yeah.
Because some of these are pretty substantially big, right? So, okay, your teaching is not continuous and therefore it is not differentiable. Okay, there's some jokers in the room too. No one put comedy as their... Yeah. I think you've done an exemplary job in teaching this course. I tried to do some cross-referencing with other professors, and none of them teach the way you do. You actually sit down and take the time to try and solidify the learning rather than just say, oh yeah, here's this theorem, oh yeah, here's its example. Instead, you've done both and mixed it together. The only real advice I would give is to maybe try and talk more about your personal thought process when approaching the proofs. Okay, good, I'll try to do that more, a little bit more. Although I'm not sure if that would even help many students, it will maybe help those who need some sort of guideline. Okay, I'll look at all of these. It's too much to read right now, but I'll look at all of these and I will use some of the feedback to improve my lectures. Okay, and then what do people want me to do more of? Okay, 35 people want me to do more practice problems from previous exams. And about half of that number of people, less than half of that number of people want me to do going through more material from the course notes. No one here wants me to talk about the half derivative, so I'll stop doing that.
I did.
Pardon me?
I did say that.
You said you want more?
Ignore the first part, but like more problems.
I think that might have been, I think these might be from the last class.
No, no, no. This is results on Math135. This is the survey. This is on Learn. I'm on the website right now.
Okay. I don't know if it does different classes.
So what is it that you clicked on that didn't happen?
The middle one.
The middle one is this class is too easy.
No, forget that. But like,
So the one that no one selected was this class is too easy. I already learned what's in the course notes and did the practice problems. Now give me my money's worth by teaching more cool things. No one clicked that. You did click that. Okay, so maybe,
This section.
I don't know. So you said that you clicked on this and it didn't work? Okay, well you can look on Learn. You can click on your attempt number and you can see if it worked, okay?
I think that might actually be from the previous section.
No, no, no. I don't think it's from the previous section. This is just one survey for all my students.
Okay.
Okay, so you said you clicked that and it didn't work. Did anyone else click something which is not, which doesn't seem like it's working? I don't know. You can double check. You can click. You can go to Learn and see what you clicked, and then yeah, it doesn't look like. Well, anyway, you're in the minority. Even if there's one person that wants that, I'm not going to be able to keep doing that because the majority of the class wants me to practice problems from previous exams. Okay? Okay, do you want to form a study group? 15 people don't want to form a study group. I'm surprised by that, but anyway, there's 11 people that do want to start a study group. And so for the people that want to start a study group, then I'll try to match you up with people that live nearby so that you can have more people to work on assignments with. Okay, and then, okay, I've always been worried about my vocal volume. I always thought that I was too loud. Well, I know when I give talks at conferences, some people complain about me being too loud. So that's why I asked for feedback about my volume. And it seems there's 2 people that think that I'm too loud, but 39 people think that I'm at the appropriate volume. So I'll try to speak a little bit to, I think if there's only 2 people that think I'm too loud and the rest of them think that my volume is between 6 out of 10 and 10 out of 10, then, I mean, it looks like 89%, 90% of the people find my volume to be okay. So then if you think I'm too loud, maybe you could sit further in the back. That's maybe a solution where I'm still at the right volume for all these people and not too loud for these 2 people. Maybe they can sit further in the back. And then about the classes, okay, so most people give me a 70, 80, 90, or 100. There's always some outliers, so that's no surprise here. Looks like people don't like Math135 very much. There's people that gave a 1 out of 10 for Math135. And overall satisfaction, okay. Okay, so I see the majority of the people have given me a 90, and some people gave me 80 and 100, and these ones, that it sometimes hurts to see a 4 out of 10 for overall satisfaction, because I am trying everything I can. It's my first time teaching 135, and it's my first time teaching here since 2008. So it was a big learning curve, and from August 20th to September 1st, I had to prepare all this. So, but I will read every single person's feedback, and I will try to improve for those of you that that thought that I was a 4 out of 10 overall. The 1 or 2 people, okay, I'm going to try to cater to everyone. All right. So maybe in a month's time we can do this again and see if I improved. Okay, and that's the end of the survey. So now let's get back to here. Okay, that's just some of this stuff. Okay, quick review of the readings. Don't expect this every time. That would be unfair to the people that want me to cover more practice problems for exams and midterms. And now that we've done the survey, we see that the majority wanted previous midterms and exams, more time on that. And there's some people that wanted me to cover more about the course notes. How about this? If you want me to cover examples from the course notes, then you let me know. Every week you can tell me these problems, these parts of the course notes were hard to understand. Can you go over this? And then, because otherwise I can't just go through the whole course notes when most of the class wants to do practice problems from exams. Okay, coprimeness characterization theorem. You all remember this one? Okay, how do we prove it? How do we prove the coprimeness characterization theorem, which is that two numbers are coprime if and only if there exist S and T such that AS plus BT equals 1? Yeah?
One direction is basically just Bezout's identity.
Bezout's identity. So if GCD of A and B is 1, then you have that AS plus BT equals 1. All right, by Bezout's identity. Then the other direction, it's an if and only if proof.
Yeah, you went and gave it away there.
Pardon me?
So you went and gave it away there.
Oh, yeah. But I'm just, yeah. Yeah, so what's the other direction? How do you prove the other direction? Yeah, whenever you want to prove that the GCD of that something is the GCD, in this case you want to prove that 1 is the GCD, then you want to prove that 1 divides A, 1 divides B, and 1 is greater than or equal to 0, right? So here we have 1 divides A, 1 divides B, and 1 is also greater than or equal to 0, so we have the GCD of A and B is equal to 1. So by the GCD characterization theorem, we have that GCD of A and B is 1. Okay, prove that the following proposition. If A and B are coprime, then A and B to the n are coprime. How do we prove that? What type of induction? Strong induction. Well, okay. In this case, just any type of induction will work, but I always recommend strong induction, because strong induction will always work whenever regular induction works. All right. A over the GCD and B over the GCD are coprime. So if I take A and B, I do the GCD of them, I call that D. A over D and B over D will be coprime. Why is that? How do we prove that?
You have Bezout's lemma, which is AS plus BT equals 1.
Yeah, so you have A over DS plus B over DT equals 1. When you want to prove a theorem about GCDs, it's often a good first choice to start with Bezout's identity. Okay? And then overall, you use the coprimeness characterization theorem, because here it's asking you to prove that two things are coprime. If you want to prove that two things are coprime, then you should use the coprimeness characterization theorem. Coprimeness characterization theorem. What does it state?
It states that A and B is the greatest common divisor of both equals 1.
If and only if. If and only if you can write it in this form, AS plus BT equals 1, right? So two things are coprime, if and only if you can write it as AS plus BT equals 1 for integers S and T. So you want to prove that two things are coprime, then you use the coprimeness characterization theorem. Next, prove the following proposition. For all rational numbers R, there exist coprime integers P and Q such that R equals P over Q. All rational numbers can be written as P over Q. You already know that. However, you have to still prove that it can be written as P over Q where P and Q are coprime. Right? So how would you prove this one? What's the logic behind it? So we have P over Q, and P and Q are not co-prime. How are we going to reduce it to lowest terms? Do you keep dividing it by its divisors? Yeah, so you keep dividing it by its divisors, and you keep doing that until you get two things that are co-prime, right? That's how you reduce a fraction into lowest terms. You keep dividing it by its divisors until you get it into lowest terms. So if you have to do some process repeatedly, then what type of proof technique are we going to use? Okay, well, in this case it's not induction, but you can use the theorems from earlier in the course notes. Okay, so the next one is, I think, the one where no, this is the one that was proven by a strong induction. That's the prime factorization theorem. But this one, you can prove it by, okay, let's see how we prove it. So if R is an arbitrary rational number, then we can write R in the form A over B. We still don't know that A and B are co-prime. So let's let their GCD be D. So we don't know that D equals 1, but we're just going to let it be anything arbitrary. B has to not be 0. That's the definition of a rational number. Then A and B are not both 0. And so D has to be bigger than 0. Okay. Well, D has to be bigger than 0 because it's the GCD. The only time the GCD is equal to 0 is if you have GCD of 0 and 0. So if A and B are not both 0, then you're going to have a positive GCD because it's the absolute value. So we have D divides A and D divides B because it's the GCD. It's the greatest common divisor. So it divides A and it divides B. That's by the definition of divisibility. We have P equals A over D and Q equals B over D. And so from division by GCD, so that was the theorem we just proved here, right? We take A and B, we divide them by the GCDs, and we get something co-prime. So let's do that. So we'll take A and B, we divide them by the GCD, and we get that P over Q, P and Q are co-prime. Okay? So that's how we prove it. We assume that the GCD of A and B is not equal to 1. It's just some D. It's just some arbitrary D. But then we use the division by GCD. That's where you take the A and the B, you divide them by their GCD, and then you get something that's co-prime. Okay? So that's the proof for this one. Co-primeness and divisibility. Now, you're all very familiar with this one, I think. When we proved that in the end, with that polynomials proof from fall 2006 midterm, we had m divides e times n to the power 4. And we knew that m and n are co-prime. So m does not divide n to the power 4. And therefore, it must divide e. You remember that one? So this is exactly the same thing. For all integers a, b, and c, if c divides a, b, and a and c are co-prime, then c must divide b. How do we prove this one? Anyone remember? Yeah?
We can use co-prime characterization on GCD thing first.
Okay, so if GCD of A and C equals 1, then we know that AS plus CT equals 1?
Yeah.
Yeah?
And then when multiplied by B? Yeah, I think so.
Yeah, well, yeah, you have the right idea. So again, with most GCD proofs, if you start with, if you know the GCD of something, then you can just start with Bézout's identity, because a lot of the time that will actually help you out. So you start with Bézout's identity on this, and the Bézout's identity for the specific case where D equals 1, you have the coprimeness characterization theorem. So you have AS plus CT equals 1. You multiply both sides by B. Actually, someone asked this on Piazza. Then you use DIC. So you have that C divides AB from the original question, and you have that C divides C, which is by definition of divisibility. So if C divides AB and C divides C, then C divides by DIC, it divides ABS plus CBT, and that matches what exactly we defined to be B here, right? So C divides B, and then B is what we have here, right? Okay, anyone lost? So you have a theorem involving GCD of A and C. It's a good idea to start with Bézout's identity. Okay? And then here you use DIC. You have that C divides A and B from, so in the hypothesis of the problem, you have that C divides A and B. So that probably means you want to use some divisibility theorem. You have that C divides A and B, and you want to prove that C divides B. So remember, Bézout's identity is what we use all the time for GCD proofs. What do we use all the time for divisibility proofs? DIC. Almost all the time we used on the midterm, we use DIC, right? So we have that C divides A and B, and we want to prove that C divides B, so then let's see if we can use DIC somehow. And with Bézout's identity, we get something, so we end up using the combination of both of those to prove that C divides B. Does anyone not follow? Any questions about this one? Yeah?
So are you saying that when we're given a GCD that we should start with Bézout's lemma?
It's a good idea. Yeah, it's not a bad idea unless you've seen the proof before and you know what to do. If you have the GCD of A and C equals 1 and you want to prove something, then it's not a bad idea to just start with AX plus CY equals 1 for some integers x and y. You know that that's true. It's another way of writing the GCD of A and C is equal to 1.
Would you ever be given a GCD that isn't 1?
Yeah. There's a lot of times when you'd be given a GCD which is just D. Let's see here. Here for this proof, we assumed that the GCD of A and B is equal to D because they didn't give us. Here we want to prove that the GCD is 1. So here they didn't give us the GCD. We just all we know is that it's equal to D. And you would do the same thing if it's. What would you do if you were given the GCD of A and B is not equal to 1? Then what would you put here?
You would set it equal to D.
Yeah.
But like, would they ever give you that the GCD is like 5? Or not?
Possibly.
Okay.
Yeah. In this course, it's rare that they'll just give you 5. They might just give you D. But it's possible. Yeah, they could definitely give you just 5. And then if they gave you the GCD of A and B is equal to 5, then it's not a bad idea to start with AX plus BY equals 5 and see if you can do anything from there. Okay, almost all these proofs use Bézout's identity somewhere. Okay, prime factorization. The proof that any number can be factored into a product of primes. How do we prove that?
Induction.
Strong induction. So that's what it says here. Strong induction. Okay. Next one, proof that the number of primes is infinite. We already went over this, right? You all remember how to do that? Yeah?
So can we use without proof that GCD of n and n plus 1 is equal to 1?
That one, that's not hard to prove, is it?
It's not hard, but like if we were to bring it on an exam.
I think someone asked that on Piazza, and I don't remember. I wasn't the one that answered it. So I think someone said that that's not a proof given in the notes, but it's a quick enough proof that you can just write it down. Yeah, so GCD of P and P plus 1, those are, that's equal to 1, but do you know the proof?
The proof? Actually, I did that.
Yeah.
Yeah.
So you use the division algorithm, you get 1 when you divide P by P plus 1, or sorry, when you divide P plus 1 by P, you get a remainder of 1, right? Yeah. And then you use GCD with remainders. So it's just a two-step proof. It's not given in the course notes, so it's not a proof that you can just use by DIC or by GCD with remainders. You should probably just write that one extra step. It's not that bad of an idea. Okay, proof that the number of primes is infinite. We've already gone over this a lot of times, right? Everyone knows this one. Did anyone see on Learn that there was an anime version of this that was posted online? You guys saw it? Okay, who didn't see it? Okay, class is over anyway, so if you want to stay for the 5 to 6 p.m. office hour, you can do that. But for now... Pardon me?
There's an anime version of a proof?
Yeah. So Euclid's theorem, this one. So anyone that wants to stay from 5 to 6 p.m. for office hours, you're welcome to. For the last 2 minutes while people are walking out, I'll just play for this for you in case you're interested. You have some questions?
I don't know if this is a stupid question.
Yeah.
But I was just wanting your opinion on this. Because I know I got this section wrong.
Yeah.
And I got the hypothesis correct.
Okay.
But like, technically speaking, I said the answer, like...
Okay, let me, so from the top, oh, this was, you proved it by induction.
Yeah, but I didn't know how to do this, and I scratched it out.
And then you got 1 out of 4, 1 out of 5.
Yeah. So I was just wondering, like...
I think I agree with that mark, because what they were doing for that mark was they were giving 1 mark for the forward direction and 4 marks for the other direction. And for the other direction, you did the direct proof, which isn't really working. So you made n equals 3, which isn't. So in one direction, you'd set n equals to 2, and you'd find that you get 5, which is a prime number. In the other direction, what you had to do was factor this n squared plus 2n minus 3 into n plus 2 times n minus 1, and then you had to show that